Okay, this is a test of the microphone and sound. Can you hear me? Does it sound okay? What if I get loud? Oh, good. That might happen. Thank you for coming, everybody. I think we're going to get started in just a couple minutes, like about 2 minutes. Okay. Visible there.
Okay, let's start session 4. This is on money final talk in English session today. This is by briandorsey, and the title is Running Your Python Application on Google Computing Engine. Please.
Okay, thank you very much. Thank you all for coming. How many of you have heard of Google Compute Engine before? Oh, kind of maybe half, a little over half. How about App Engine? App Engine, okay, everybody's got App Engine. How about, they're different. How about cloud storage? Google Cloud Storage, a blob store. Okay, and has anybody used Compute Engine here before? Oh, a couple people, okay. So quickly, my name is Brian. So each of these boxes represents one virtual machine, a single core computer. I've made one request to start up these instances, and then Compute Engine is beginning to reserve machines for me. So the blue is staging the virtual machines. Yellow is copying out the image to the machine and then starting to boot. So that's staging. And then once they've gone green, they are up and running their boot scripts and ready to run your software. So you can actually SSH into the virtual machine at that point. So we're trying to make the whole system fast enough that you can the service that make that very easy, and then some next steps. So, but I wanted to make a quick little diversion. I don't need to introduce Python to this group, I don't think. But I just wanted to highlight that it's one of the standard languages at Google. We love it. It's fully supported in the Google Python API client. So if you've ever used the Google Python API client for any other Google API, Compute Engine works exactly the same way. So if you've got experience using that already, then you already know how to talk to the Compute Engine API in Python. And our documentation examples almost always include Python. We've written tools in Python. We release open source. We love Python. And so, of course, if you put Python on top of Compute Engine, it's all awesome, right? So as I go through this talk, since this is running Python applications on Compute Engine, and it's basically Linux, most of the talk is about Compute Engine. But I want you to think about what it means to be able to forget about infrastructure, mostly. You know, where you can actually automate the infrastructure with software as you're building your programs. So think about how these things can save you time to spend writing your software instead of managing the environment. Okay, so first off, everything I'm going to show you is built on top of the APIs and client libraries. All of the Compute Engine APIs, like many other modern Google APIs, are HTTP and JSON-based. And we have client libraries in about a dozen languages. Python is fully supported. And then we build our tools on top of that. So I'm going to show you a command line tool in a moment called gcutil. That uses the API. The Cloud Console that I showed in a moment ago, and I'll show more, also uses the API. We have partners that help with auto-scaling and other things like that, they use the API. And your software can control Compute Engine directly, either from inside Compute Engine or from App Engine or from anywhere on the internet where you have the right security credentials. So what does this look like? So the command line tool is called gcutil. And from this tool, you can do nearly anything that the Compute Engine API supports. So for example, we can add an instance. And we'll call it PyCon, because of course. And since I didn't specify, it's going to ask me a few questions that it absolutely needs to know. First question is where to run. I'll talk about zones a little bit more in a minute, but we have zones that are part of regions, and they're close by, and then regions are in geographically separate locations. So they should be unlikely to be affected by natural disasters together, for example. So we're going to pick US Central 1A, because it doesn't have any maintenance scheduled. I apologize for the small window in the demo. When you're on your developer machine, it'll look a little better. I'm going to pick a single core instance. That was this one from up there. And I am going to create a persistent disk. Actually, no, I'm not going to create a persistent disk. And I'll talk about those a little bit later. So then it goes and calls the API, and it's now pulling the API to create this instance. One thing I'd like to point out here is if you get an instance ready from the API, every call after that will get instance ready. You won't get kind of eventual consistency in the API calls. It's down to a given zone, and the zone knows the state of your instance. So that'll come up correctly. So we've got our instance up, and again, I apologize for how this output looks here. So how do we get into the instance? We can just SSH into it. Now, that sounds awesome, right? But like, how does that work? So I have used OAuth 2 to do a verification that I own the project that we're talking to. So gcutil knows who I am, and Compute Engine can verify that through the OAuth tokens. So since it's done that, it can also manage a set of SSH keys on my machine and put the public keys up in Compute Engine so the instances know that I'm allowed to connect. And since it's done all of that for me, I can just say, gcutil, handle the SSH keys for me, and log in. And we're ready to go.
Are those keys separated from the Python configuration?
Yes. So those are Compute Engine keys that are generated on first use. But you have some options. You can use your own keys if you prefer. And you can add new keys to the Compute Engine configuration. So we're logged in, and my host name is PyCon. So I also wanted to point out that the name you set for the machine is the same as the host name, is the same as the internal DNS name. So within your private network on Compute Engine, the name of your instances is DNS. So you can ping PyCon and have that work. For instance, I have an instance called dev. That's my developer instance, and I can just ping it by name, and it connects there. And this is a real machine. So I can install, Python requests, the best way to use HTTP, and get coding, start using Python. If we really hope the Cloud Console and network's working, excellent. We can see these same instances here. I'm actually going to make this window a little bit bigger, and we'll look at just the right-hand side for a second. So here's the instances that we created. That's my developer instance that's been running for a long time. Here's PyCon. Here's all these instances from the quick start that I forgot to shut down. So we can go back over there, and they're all up and running now, so we'll reset those, and then those will go away too. But so this is what we call the Cloud Console, and it is becoming the new place for interacting with all Google APIs. So if you're using Calendar API or YouTube API or other things, over time you'll be able to use them all through this same interface. And for the cloud, we have a special set of administrative web pages that you can use to run things. If we look at this instance that we just created, it's a 1 CPU, almost 4 GB of memory machine in the zone we picked. It has what we call an ephemeral. That's an IP address that comes and goes with the instance. And you can also make static IP addresses. So it has both an external and an internal IP address. The external IP address is optional, that sort of thing. So we'll get into some more details there. But one thing I wanted to highlight is when you create an instance, one of the things you can do is specify a tag. And this tag is just a little piece of text that can mean whatever you want in your application. So you can query all of your instances and see what tags they have. You can ask in a startup script, which I'll talk about later, what your tags are and make decisions about what to install or what to run. And our networking, the firewall rules support tags. So I'll talk about that later. And you can also basically control all of Compute Engine through this web interface, if you like, through the command line interface and through the API. So here are the zones we have, the same 5 zones we saw earlier with the same information. I should highlight that each of the zones goes through a maintenance window about once every 6 to 9 months. So when you're building an app on Compute Engine, you should be thinking cloud style, where your instances can move from one zone to another, or that their setup and configuration is scripted rather than manually created. And I'll talk about networks and metadata and load balancing and disks in a few moments. OK. So for the virtual machines, we're now next section of the talk. Virtual machines. So for our standard machines, we basically offer 1 to 8 cores of virtual processors, so 1, 2, 4, and 8. And then you can get them with different balances of CPU to RAM. So you can get instances that have more memory or instances that have more CPU relative to memory. And that just changes the prices a little bit. To give you a bit of an idea of kind of where this comes out, 30 days of a 1-core instance is about $83 US. So 100円計算で8000円かな? And we also offer micro instances. So these are great for development work, for experimentation. If you make software that sets up 100 instances and you want to test it, you can use the very affordable micro instances to make sure everything works correctly. So these are more like $14 for 30 days. Or a weekend of hacking, so like 16 hours of hacking on the weekend, is going to be about 30 cents, or about 30 yen. So 16 hours is going to be about 30 cents with these guys. So actually, I forgot to mention. So CentOS and Debian, so your software probably works on Linux already, but that's what we have. And the CPU and memory are dedicated to your virtual machines. There's no oversubscription at all. So if you pay for a 2 CPU machine, there's no other virtual machines using those 2 CPUs. Except on the micros and the smalls. So that's part of what makes them affordable. So these share CPU. I also wanted to point out our billing page talks about hourly prices, but we actually bill down to the minute with a 10-minute minimum. So that part's important. So once a machine has been running for 10 minutes, if you run it for 11 minutes, you only pay for 11 minutes, not 1 hour. So if you want to set up Hadoop, for example, and run it for 15 minutes, you'll pay for 15 minutes for each instance rather than 60 minutes for each instance. So that's 4 times cheaper. OK. So before I get into block storage a little bit, Compute Engine is part of cloud. So in cloud, we have App Engine with its data store. And you can now get to the App Engine data store outside of App Engine. So you can get to it from Compute Engine or from your own machines. We have Cloud SQL, which is managed MySQL, so you don't have to worry about replication and backups and that sort of thing. And we have cloud storage, which is object store, a blob store, so key and value. And the value can be like 5 terabytes or so. And I'd love to talk about that later, because I work on that too. But there are 2 kinds of storage we have in Google Cloud that are only on Compute Engine. So, and they're both Linux block devices. So they show up to the machine as a block device underneath the file system. And so there's 2 kinds. So the first is Scratch disk. And you can think about this as local storage. You enable it by choosing a machine type that has -D on it, and it will be just slightly more expensive. So this is for truly temporary data only. Like, you do not want to use this for anything you care about long term. It's for, say, transcoding partial files, or for storing log files right before you get them right off the disk, things like that. And the higher CPU instances have more space. So the billing is part of the instance. It's all together in this case. And then we have persistent disk. And persistent disk is just awesome. So I'm going to talk about this for several minutes. It's for really almost all of your data that isn't temporary. So things like database files, anything that you would normally store on disk on a physical computer and expect it to stay around, the stuff you have on RAID 5 and 6 and RAID 10 plus 1 or whichever variation you use, that goes on persistent disk in Compute Engine. It can be a data partition. It can also be the root partition. So you can boot off of persistent disk. And this is how you get long-running, or instances that you can move around nicely and keep their configuration. So if you boot from a persistent disk, you have a virtual machine, and you say, oh, I want more memory. You can just reboot so you delete the instance and create the instance from the same persistent disk, and you get more memory. You choose a different machine type. And they have extremely consistent I/O. So I highly recommend running your favorite brutal disk tests against this and see how it turns out. It's explicitly designed, or it's designed for working with databases and other I/O patterns that are very sensitive to latency. So you want your latency curve to just be very smooth, no like weird spikes at the end, right? That slow everything down and get things behind. So it's designed with that in mind. And the billing works a combination of the size and how often you hit it. So millions of operations. So persistent disks live at the project level. You create a persistent disk, and it lives as part of your Compute Engine project. And then you can boot from it or not. The Scratch disks are permanently attached to the instances. And I have a whole slide for this, because if you put data on a Scratch disk and it goes away for any reason, that data is gone. There's nothing our support team can do to help. So use persistent disk. That's what the big X means. Use persistent disk. And there's 3 main things that persistent disk is very useful for. So I mentioned booting from the persistent disk. So you've got this hard disk in the sky, in the cloud, basically, right? And you can boot an instance from it. You can delete the instance. You can boot another instance from it. It's the same computer. We also can use persistent disk as attached storage. So you can have an instance that's up and running. You can create a persistent disk, attach it to that instance, read and write to it, detach, plug it into another instance, move it around, that sort of thing. So it's kind of like a super-powered USB drive. And this one on the far right here, you can attach the same persistent disk to tens or hundreds of instances read-only. So what you can do is you can attach it read-write, prepare a bunch of data, detach it, and then attach it to 100 instances. And they all have read access to that information with just a metadata transaction. So there's no copying going on. You can just make the API call, and when it returns, they all have access to that data. So that's very powerful. I wanted to just talk a little bit. I've got the link in a moment, but there's a whole talk on persistent disk. And one of the ways it gets this very fast consistency is that the actual blocks are stored on multiple machines across the Google data center. And it does a competitive read request across the instances. And the fastest response comes back to your virtual machine. So if you make the request, and 3 of them come back, and 1 of them's slow and 1's fast, that's the one that goes to your machine. So that's one of the techniques it uses to make your machines feel extremely fast. Also, all the data is encrypted all the time. So it's encrypted in flight. It's encrypted at rest on disk. The keys are managed by the service. It includes multiple copies of all the keys, of all the data, and it does checksums as it moves the blocks around. So you shouldn't see, a block that you haven't read for a while is suddenly bad or something like that. And you can take snapshots of persistent disks, both when they're disconnected and when they're connected to an instance. So this takes a point-in-time record of the logs underlying the persistent disk, so it knows exactly at that moment what the state of the disk is. And it makes a copy of that and stores it in Google Cloud Storage. And then you can take another snapshot and have that at another time. So you can take a daily snapshot, for example, and then you can create new persistent disks from those snapshots and see what the state was a week ago or a day ago, that sort of thing. So you can use this for backups. You can use it to copy or migrate the persistent disks from one zone to another. Persistent disks are limited to one zone at a time. So if you want to move a disk from one zone to another, take a snapshot. Snapshots are global, and then you read it. You can create a new persistent disk in any zone, just directly. Also, the snapshots are only billed for the space actually used. So if you only use 10 megabytes out of a 10 gig persistent disk, you only pay the 10 megabytes. And then if you make a second snapshot, you only pay for the data that changed in the second snapshot. So you're only paying for the actually unique data all the way through in snapshots. And yeah, so I just wanted to re-say that the snapshots are global, and you can restore them anywhere in the world. And this is one of the primary techniques for moving instances between zones, if you need to for any reason. So from the command line, using gcutil, it kind of reads like you'd expect. I'd like to add a new disk that's 100 gigabytes in this zone and call it that name. Or give me a new instance and attach these 2 disks to it when you create it. And you can attach a disk to an existing instance, like we talked about. And this is how snapshots work and creating persistent disks from snapshots. So it's very easy to automate with scripts. And all of this is available through the API, so you can do it from Python as well. So basically, use persistent disk, test it out. It's really amazing. Give it a try. Oh, and this link, I will have a link to the slides at the very last slide. And this link is to a Google I/O talk only about persistent disk, where he goes, the tech lead goes into great detail on how it works. So there's that. Deep breath. And next, you didn't just see the to-do on there. No demo. OK, so the networking that you get in Compute Engine is, so all of these instances live on the internet, right? They live on Google's infrastructure. And all the networking works over TCP and UDP. So that's how you hit it. Only those protocols. So if you want to use something other than internet protocols, this isn't the right solution. The IP addresses, each instance can have a public and a private IP address. And the public ones can be static. So you own the IP address, and you can have different instances attached to it at different times. Or they can just come and go with the instances. And I mentioned that the internal addresses have automatic DNS that match the instance names. So that makes things easier to write scripts where your instances cooperate, as long as they know their name or the names of other things, like you have a standard name for your main database server, things like that, they can hit it. And we have firewalls and kind of network groups that I'll talk about, and also routing and load balancing. So let's talk about network stuff for a bit. So firewalls. First off, all of these instances, even when they have a public IP address, are firewalled off, and the only thing allowed is SSH over port 22 by default. So you can get in. Nothing else. And when you want to allow more access, that is basically you set up which sources. So 000, for example, is the whole internet, and TCP/22 is SSH. So this is the built-in rule. You could also add a new rule that says, for all instances tagged web server, allow port 80 from the whole internet, things like that. This tags is that tag I mentioned as you create the instance. Also, you could basically say, you can specify a tag on the source as well, which means it's limited to other compute engine instances. So you can say, if I've got an instance that's tagged Redis, it will only accept TCP 6379, which is Redis, from instances tagged web server. So you can set up rules so that your network is partitioned off into different pieces. So the public can't talk to your Redis server, for example. And gateways are kind of the opposite. So when you make outbound requests, TCP requests from your instances, if you set up a gateway, so normally that goes through the compute engine infrastructure out to the internet. If you enable a gateway, you can force all the traffic to one of your instances, and that instance can do whatever it wants with the traffic. So you can set up VPN software to connect to your internal network. You can set up proxy servers. You can set up your own outbound rules so that your instances are not allowed to talk to the internet except in the way that you want. So that's what this is. And then load balancing. So it has a built-in load balancer that works at layer 3 of the network stack. So it works with TCP and UDP. Every connection made on TCP will hit one of your instances in the load balancing pool, and then all the packets during that connection will go to the same instance, but the next connection will go to a different instance, or could go to a different instance. So it works at that level. And this basically works where you define a group of instance names and what the rules are for whether they're healthy. And then the load balancer handles removing and adding those instances to the actual traffic. So you set a public IP address, and it comes through your instances, and only the healthy instances are sent traffic. And so healthy, what does that mean? Basically, the load balancing infrastructure makes HTTP requests to your instances, to whatever URL you specify. And if you return a 200, it's healthy. And if you return any other code or anything else, then it's unhealthy. So your application can define health for your instances. And you can also define how often that's checked. If you have really stringent needs, you can check a lot, and that sort of thing. So there's that. So what is the end time? I'm sorry. How much time do we have? 7 minutes? OK. Moving on. So moving on to building and porting your applications. If we have time, we'll come back to that demo. 20 minutes? OK, we're going to do the demo then. OK, so I've got a demo of load balancing. And basically, we'll have our instances here. And this demo, we're going to start 2 sets of virtual machines. So we're going to have just one instance on this side and a whole cluster on the other side. This is currently starting those instances for real. They're booting up using a startup script, which I'll explain in a moment. And then using that information from the startup script, they're downloading or they're using the metadata for a fractal generator, compiling that, and starting that web service. And then when we see the check marks, that has actually been compiled and is up and running. And once that happens, we're going to use the Google Maps API to actually look at the fractals and zoom around them. So we can see these coming up over here in the Cloud Console. So we've got our fractal cluster 0, 1, 2, 3, 4, and then we also got this single instance there, and that's just what they're named. OK, so we've got some checkboxes there. We'll show these maps and our checkboxes, and if we zoom around, you can see more machines can render fractals more quickly than fewer machines. Yay. But these are each hitting, each of these is just hitting one IP address, and the right-hand side, Google's load balancer is handling that. So we can add a few more VMs, and with a narrow screen, they'll be underneath the map, but that's OK. They still will boot. And we can keep zooming around in here, and this will all keep working as our new instances come up and get added to our pool. And then I can go be mean in the background and say, fractal cluster 3, these are tagged, by the way. I actually don't like this one. I'm going to delete it. So we delete that one. And when we come back over here, it's refreshed, it goes red, and our fractal demo still works fine, even though one of the instances has gone dead, and we're starting up new instances. And all of that's handled by the health checking in the load balancer. And we can hit a harder one. Watch that come up. And now we've got some new checks over there. You can check on the status of what load balancing thinks about your instances and their health by coming in here. This information is also available in the API. And we can see that 3 is unhealthy, and some of these don't exist. That sort of thing. So there we go. So that's the demo. OK, so a little bit about porting your applications and building applications. So you kind of have two. So sometimes you have existing applications, and you need to run them in a cloud environment, or you want to. And sometimes you're building a new application. So when you're building a new application, I really recommend checking out some of the features of the different cloud platforms, because they can save you a lot of time. And 2 that I'm going to talk about here help pretty much in all cases using Compute Engine. So before I get into that a little bit, if possible, as you're making your applications, try to think about the instances themselves as disposable. Like, you can throw them away. So if you have 10 instances and one of them dies, just like that load balancing demo, it's OK. Because there's nothing saved on one instance that I really care about. It's either spread across all my instances, or you can store data in one of the services that either Google makes available or other people make available. So store that state in the App Engine data store, Cloud SQL, cloud storage. And then if any instance goes down, Google's handling keeping all of those services up, so you don't have to worry about one particular instance. Persistent disks also help a lot. Take snapshots, move them between zones, that sort of thing. And when your application is large enough that it makes sense, try to run always some of your instances in different zones and different regions. And if anything bad happens to a Google data center, then you won't worry about it, because there'll be others. I'm going to quote Adrian Cockcroft from Netflix. They are very advanced users of cloud technologies and basically automate everything. You want scripts and automation for everything. If you're manually setting up the machine, if something bad happens, it will take you a long time to recover. Whereas if you write the script up front, then you can just run the script again, and you're good to go. So to help automating, Google Compute Engine has this metadata server, and it's basically a key value pair server that's intended for configuration data. So if you want to say, where is my database instance, or here's the startup script for this instance, or any information that your configuration depends on, give this a try. If you're familiar with Zookeeper or DoozerD or etcd, any of those things, kind of a similar role. But it's configuration information as a service. So if you set the configuration here, then you don't have to worry about your instances. And there's both project-wide metadata and instance-specific metadata. So the project-wide metadata can be the configuration for your whole service, and the instance for configuring that particular instance. So if I add an instance, so I use gcutil, add instance, and I just say metadata equals foo bar, so key value. That starts the instance. I go ahead and SSH into the instance. Go ahead and get into the Python interpreter. And there's this server that exists inside of Compute Engine only, that is only visible to your instances. And you can get that same value back out directly there. So you can do this from Python. You can do it using curl if you're using a shell script. So you can set an environment variable from curl. You can use it from Python anywhere. Really handy. And Google uses this metadata server to implement startup scripts. So this is a bash script that runs immediately once the machine is booted. So as soon as the machine is healthy, it runs this script. And this script can do anything you like. You can use it to apt-get install packages, to run software. You can use it to bootstrap Chef or Puppet or Fabric or SaltStack, whatever your favorite automation tool is. And basically, it's the kickoff point for configuring your instances. And a small example would be, sudo apt-get install nginx. This command, gsutil, is cloud storage for Google Cloud Storage. And this does a recursive copy of all of this data into that directory. So it grabs from a service the actual state data and stores it locally. And then you start the instance, and you say, use this startup script as the startup script. And when the instance boots, it immediately runs this script and does whatever you say. This being scripts, you probably won't get it right the first time. I never do, ever. So if you want to debug it, go ahead and log into your own instance. And this is the log file, which has the output of these scripts. So if you want to see what it did.
That depends on the distribution.
Ah, OK. This is where the log file is on Debian. Where is it on CentOS? Anyway.
Google on CentOS and that script log on Debian.
Ah, OK. My apologies. It's different per OS. That's confusing. We should change that. OK. So you can use this as the base of automating your compute engine. And then beyond just one instance, usually your application runs for a long time, right? You want to start up instances and shut them down. If you get more traffic, have more instances. If, whatever the needs of your application are, if one of them dies, you want to start a new one up, that sort of thing. So you've got several options here. You can use the Compute Engine API from App Engine and use App Engine cron to just check on your Compute Engine and say, oh, my rules aren't met, add new instance or delete instance or anything you want to do. So you can code your own, anything. You can also use Chef, Puppet, SaltStack. We have a partnership with RightScale and Scalar, who do cross-cloud automation and orchestration. So you can do that. But all of these do similar things. They manage your configuration, deploy new instances, scale up and down, that sort of thing. So it's worth looking into one of these as your application gets bigger, for sure. And I wanted to just point out, I've got a very, very small example of this from App Engine here on GitHub. And we can take a look at it at the end if you like, or I'd be happy to talk about it. But it's basically about 50 lines of Python, and it runs in cron. And any instance that's been alive for more than 8 hours and doesn't have a production tag, it kills. So I've been in the position of accidentally leaving instances running for a very long time. And if you run this software, it will delete those instances if you're not using them. So, and it's a good example of simple orchestration. Okay, so a couple final comments. The whole Google Cloud platform is evolving very rapidly. Google has been doing cloud since before the term, for its own products. And we're now beginning to make that available for all of you to build software on. And any time you spend learning Google Cloud products now, the products will keep getting better and better and better. So that is time well spent, in my opinion. And we can imagine your applications running inside of Google data centers. But I want to take a step back. So everyone here's a programmer, right? So you all program in Python. So I think you have superpowers, like literally like superpowers. Because you can take your ideas and your thoughts and make them work outside of your head. Like they can do things when you're not around. And I want you to think of, so we have Python, which makes it easier to take thoughts and write them down. And there's more and more activity in different deployment options, different hosting options, different cloud platforms, and especially in web frameworks and databases, all this activity going on. And I encourage you all to learn about lots and lots of these different things, because every one of them is a new step to make you stronger and allow you to focus on writing code that does things, build things that you care about. And all of this is about that. So it's like about building your things. So yeah, Q&A. So yeah, lots of stuff here before the Q&A, I guess. Tomorrow, Takashi-san is going to be giving a talk about using Compute Engine and App Engine together, using the new VM-based backends that are Compute Engine inside of App Engine. So you get all of App Engine, but running on Compute Engine. I'm going to be at the sprints. So if you want to try to use Compute Engine and want somebody nearby to help, I'll be happy to do that. And everyone at PyCon APAC gets $2,000 of free credit from Google. So if you go to that URL and use this code, that's $2,000 for 6 months. So go compute. Yeah. So thank you all very much.
We have 5 minutes for questions or comments. Any question, comment? 日本語でも OK だそうですよ。
Yes, quick question. Any plans for a Tokyo data center?
Tokyo data center.
Yeah.
APAC data center. OK, so we don't have anything to announce today. We're definitely looking at where we can expand. You saw that there's actually just 5 zones right now.
Yeah.
So you can expect that we will be expanding over time. And we're definitely listening to where people want to use it. And so we'll do our best to make everybody happy there.
Cool. Thanks.
So,
Thank
kind
you.
of a non-answer.
Thank you.
Any other questions?
I worked as an English teacher. I'm really patient.
いいですか？インストールできる オペレーティングシステムはIA アーキテクチャだったら何でも選べるんですか？
So let me repeat the question
In English.
in English, and correct me if I'm wrong. Is it possible to install any operating system as long as it matches the processor architecture?
Including Windows Server?
So that's the question, correct? Is it possible? Okay, so right now, you have to use our kernel. So Compute Engine has a Linux kernel that it injects into your image at boot time. And that's what I have to say today. So we have Debian and CentOS, and you can actually change the distribution out to anything that works with one of our kernels. So we have documentation for doing that for Linux. We don't have anything to say right now about Windows.
Thank you. Any other questions? So I'd like to close this session.
Okay.
Which VM machine are you using? It VM machine or several kind of web architecture exist to you, or what kind of VM?
Okay, so we are using KVM plus special sauce. So there's a KVM layer and then a lot of Google custom infrastructure underneath that. So we're using that as the bridge to Google's architecture internally. So, yep. Awesome.
Okay, now to close the session. Thank you very much.
Thank you all very, very much. And I'm happy to talk one-on-one.